use this data to define the model. So
must be some typo there.
yeah.
Okay.
So so what's the if we use this data to define the Levin model, we see each object in the matrix. So each string type actually has two labels. Like here it's like a E1221, E22. So I will call this each number a half label. So to view this more conveniently, I will draw a double line in a trivalent graph in the Levin model. So in the original lattice, it may be any trivalent graph, and now I replace this each line in the trivalent graph by a double line, and when I put the degrees of freedom coming from these string types, I will put like an E12. I will put two numbers on each of the link. So if I do this, what we have found is that it's related to the symmetry protected topological phase model. So in this example, the signature symbol condition becomes the 3 co-cycle condition. So in this example, I will set L0 to be I guess 0, 1, 2. 0, 1 to n minus 1, and I write on the signature symbol condition which is defined here. So the conclusion, the result is the signature symbol only depends on 4 half labels: alpha, beta, gamma, and delta here, because of the fusion rule. We have written down here.
This protocol typically will not have this kind of symmetry. So in your previous protocol, you have this kind of symmetry for the GC.
Yes, that's right. So we believe this can be extended to a model with a branching structure in the lattice.
But in the original model, this 6J symbol actually has only 3 degrees of freedom, but now there are 4. Is it true?
Yes.
So it's not a 3 co-cycle anymore.
So this co-cycle is so 3 co-cycle. You have 2 ways to write on the 3 co-cycles. Just like in the SPD model, we use
How many independent degrees of freedom alpha, beta, gamma, delta? Are there 3 independent degrees for these 4 hours?
in the SPT model, when we do the partition function, we put the glue elements G0, G1, G2, G3 on the vertices. Then in the partition function, each constituent is a function of 4 glue elements.
Yeah, but they are not all independent, so that's why you can still write it as a 3 cocycle.
So if you put the glue elements on vertices, you have 4 glue elements. But if you put the glue elements on the links, then you have G0 inverse G1, G1 inverse G2, G2 inverse G3. Then you can define a 3-core cycle in another way. G2 inverse G3. So this is all. Yeah. So this way when we write on the 3-core cycle, it has 3 glue elements, and sometimes we call this the homogeneous 3-core cycle, and this is the inhomogeneous 3-core cycle. If the tetrahedral symmetry is satisfied, to answer Gu's question, then this is a symmetric based model. So but here I want to go to a more complicated extension. So if I choose if we choose a finite group, and we can define a multi-fusion category in this way. So if we choose a more complicated case like C, the category, the input data is from Ising category. Ising category means you have 3 string types, 1, sigma, and psi. And this data means you have the S matrix, which is a 3 by 3. It's 1 square root of 2, 1, 1, 0. And topological spin for each string type. Then by this data we mean the Ising category. So to define the model, we have the tensor description, which is the sigma symbol. G, I, J, K, L, and N. And a quantum dimension, and a fusion rule. So we can use this data to define the Levin-Wen model. But here we can do the we can do a little bit extension. We put one psi and sigma into the 2x2 matrix, just analog to these two matrices I just introduced. Then in this extension, I label each object by 0 or 1, which is the matrix index. Yes?
What is
Sigma is the icing onion and psi is the marginal onion in the icing theory. So it's a notation. Sorry? Who write the matrix? Right. So one way to do that is you can derive this data from the SU2 quantum group representation, and then so it's a quantum group representation. SU2. K level 2. So this is a quantum group. And when you write down the representations of this quantum group, you find that there are 3 decomposable, irreducible representations. And then you can derive the topological spin of each representation and the mutual statistics between each of them. And then you can define the icing data by these 3 representations. So, in general, more generally, we can consider a little more complicated extension that given this icing category, and I divide these 3 string types into 2 sets. So here I will call C1 is 1 psi, C minus 1 which is sigma. And now I will write on the fusion rule of this category. The sigma tensor sigma is 1 plus psi. Then I divide these 3 string types into 2 sets. And the fusion rule between these 2 sets form a Z2 group. Because if we associate minus 1 to sigma, then minus 1 equals to 1. So you see the fusion rule satisfy the group multiplication. So in general, if you have if this is associated with the group elements G, and this is associated with group elements H, then these 2 must be associated to GH. So this is called the grading. It's called the graded category. Meaning you can associate group elements to each string type. Then I define the L0 to be 1 and minus 1. The unit set L0 to be the Z2 group. And we have two copies of one side sigma in the extension. So for example, like this. Then what we can do with this extension, if we put this data into Levin-Wen model, then what we have is a model with the original data from Ising category, and also with the symmetry group. Sorry, I would say with the finite group Z2 in the model. And how does this finite group and the original category enter the model, and how they interplay with each other? So I want to talk about this right now. So where's the original string types from the Ising category? So they are still string types living at the links. Remember that when we define the model, the degrees of freedom are living at the links. So this is not changed. But the actual thing, the finite group is at the plaquettes. So like we have 1, we have minus 1. Inside each plaquette. So you have two types of the degree of freedom. So this is in the Z2 group. And these are coming from the Ising data, Ising category data.
So this corresponds to some hierarchies here. How you have some no.
And the Hamiltonian is, and the Hamiltonian is defined in general we have two terms, Q and B. Q is defined at the vertices, and BP is defined at the plaquettes in terms of the signature symbols. And now let's.
So how symmetry is the
Symmetry.
yeah, what is action? How symmetry
Oh, how symmetry acts. Okay. Okay, I will talk about that. So I think you're asking if we have the quasi particles here, and from the Hamiltonian, how can we see this Z2 group is acting on the quasi particles?
No, I'm asking the action of symmetry. You know, what is a, you mentioned Z2 symmetry group, so how you define this symmetry action?
Symmetry action of the Hamiltonian.
On the Hilbert space.
Okay. So you're talking about the global symmetry. So okay. So the state, the symmetry is acting on the group elements and the plaquettes, just like the SPT model. No, the degrees of freedom is coupled to the link.
But the symmetry action. So the index of the link are singular on the symmetry.
Yes. Yes. So now BP. So now if we have the -1 here and we have 1 here, then the link has a gradient determined by the two group elements on both sides of the link. So, for example, if we have -1 here and 1 here, then this link carries this link is associated to the group elements -1. So we associate this group elements to the link to indicate the coupling of the group elements to the degree of freedom on the link. So yeah. So basically, it's very like the original Levin-Wen model defined in terms of the icing data. But we have the group elements and the plaquettes, and also the group elements are they are coupled to the I would say to each string type and a link. We associate a group element, which is determined by the difference between the two group elements across the link. So, yeah. So, what does this model? So I will claim this model describes the symmetry in rich topological places. So, how do you see that? So now I will go back to the slides. So in the Levin model defined in terms of the icing data, if we divide the three labels into two sets, the one psi and the other set is sigma, with this Z2 grading, then we will see in the first set, 1 psi, it forms as a Z2 subset. That means 1 psi, it forms it carries the Z2 fusion rule. It's closed under the fusion. So if we forget the second set, we just use 1. We restrict the Hilbert space such that each link is labeled by 1 psi. Then this model is just the Levin-Wen Z2 model. And the quasi-particles are quasi-particles are described by the quantum double of this Z2 data. So now I will label this Z2 category by C1. One means the group elements. 1. Now if I associate, if I put the group elements at a plaquette, and we add more degrees of freedom to the model, then this is equivalent to associate a Z2 flux to each plaquette. Then the quasi-particles in the original Z2 model, the quasi-particles here, we will attach the Z2 flux to these quasi-particles. Then these quasi-particles are described by the extension, so they are no longer, I would say, there will be more than 4. Since originally we have 4 quasi-particles. When we attach the Z2 flux, then we may have 8, sometimes we may have 7, we may have less, like 6. So and in the Hamiltonian, we also have the action BP sigma in the second term, which is new, because originally if we use the 1 upside to define the model, we do not have the operator coming from sigma, and so the Newton this sigma in the enters the local operator that will give us local action on these quasi-particles. So this local action, local operator will act on these quasi-particles and it may shuffle these quasi-particles. So to understand how to understand this phenomenon, it may be complicated, since what we only know is before this local action, before we attach this Z2 flux H plaquette, we have the quantum double of Z2. But after this extension, what we do with these new quasi-particles. So what we do is to promote this local action into a local gauge symmetry. So that means these local actions form a Z2 group. And if we promote this Z2 action into a gauge symmetry, then these